Hi, and welcome to Module 5 of Video Lecture 3. Having gone through and defined the derivative both intuitively and formally, now what we're going to do is talk a little bit about how to actually calculate it from first principles, so we can apply the knowledge that we just gained. Okay, so let's remind ourselves what the definition of a derivative is. It's the limit as h goes to 0 of f of x plus h, f of x divided by h. And I changed the x1 to x, it doesn't make a difference. And again, you'll sometimes see this written as h, sometimes as delta x, because the difference between x1 and x2 from the previous module, they're all the same thing. They're just something you're taking a limit as it goes to 0. It doesn't have any intrinsic meaning. So again, you can have delta x, replace h with delta x. They all mean the same thing. We'll use x because it's easier to deal with notationally. Okay, so here's our definition of a derivative. How might we go about calculating one? Let's start simple. How about a constant a? What if our function is a constant a? How might we calculate a derivative? Well, all we have to do is plug into that actual formula. So we have a limit as h goes to 0 of a minus a. Now, why are they both a? Well, f of x is a, so the second one's definitely a. What about the first one? Well, the first one, f of x is a, f of any x is a, therefore f of x plus h is also a. So any f of x is a, and they're both a divided by h. That's 0 for any h, so limits are relevant. And you get the derivative of a constant is 0. That's good, because if you drew a constant graph, say like that, what's the slope? It's 0. So the derivative spits out the slope as it's supposed to. And the derivative of all constants is just 0. What about a linear function? Okay, this is a little more complex. Let's start again. Well, how do I plug in x plus h into a linear function? Well, it's a times x plus h minus ax is the function itself, divided by h. Now you start seeing a pattern here. Well, ax, so I can distribute that out and get the limit of ax plus ah minus ax over h. The two ax's cancel. That leaves the limit as h goes to 0 of ah over h, which is just a. Again, the limit doesn't actually show up. This is the general pattern of all these calculations you'll find. The leading term in x will cancel with the minus f of x, the leading term in that, so that'll always go away because there's never an h in the leading term of the x plus h function, of the function of x plus h. That'll always cancel. The second term, the second highest power of x, will have an h attached to it. The h's will cancel with the h in the denominator, leaving the second highest term in x, and then all the rest of the x's, all the rest of the powers will have higher powers of h in them, and that will vanish when the limit is taken. I'll show you how that works in practice in a second, but just note that before we move on, the derivative of a line with intercept 0 is just the slope of the line, as it should be. What if we added a constant in there? Well, if we had ax plus b, that would change nothing. So you have a times x plus h plus b minus ax minus b. The b's cancel as before. So again, you just have ah over h. So there's a limit here. I'm going to stop writing the whole limit out to save myself some effort. There's a limit here, and that just equals a. So again, the intercept doesn't matter. The constants don't matter. The slope of a line equals the derivative of the function that represents that line. Okay. Now, let's do a little more complicated one. What about the function, let's see, ax squared plus bx. We'll drop the c. Oh, we'll put the c in just to get more practice. Okay. There's a quadratic function. How do we differentiate that? Well, it's the limit. Now I can plug in x plus h here. That's a x plus h squared plus b x plus h plus c. Now minus the function itself. That's ax squared plus bx. Oh, sorry, it's minus bx minus c. Okay, all over h. Now what do I do with that? Well, I have to expand out the x squared and distribute out the b. So if I do that, I get ax squared, it's a leading term in x, plus 2axh, the second highest term in x, plus ah squared, and that's the third highest term in x, plus bx plus bh plus c minus ax squared minus bx minus c all over h. Now note what cancels. The leading term in x, in every term, it's going to cancel. So ax squared cancels with negative ax squared, bx cancels with negative bx, and c cancels with negative c. So the leading term in x in every constituent term in the function is going to cancel when you subtract out the function itself. That leaves you with stuff that has an h in it. Let's write that out over again. Well, we have 2axh plus ah squared plus bh over h. Now I can divide through by h. And what do we get? We get 2ax plus ah plus b. Note that two of those terms have no h in them at all, so limits are relevant for them. The middle term here has an h. It's ah. The limit of ah as h goes to 0 is 0. So that term goes away in the limit, leaving you with only 2ax plus b. So again, let me take a step back and go through these steps again. First, step 1, I plug in x plus h to this function here, to this function, and then that's f of x plus h. Then I subtract the function itself with no h. That gives me this thing here. The second step, I expand out all of my terms. So if there's an x plus h squared, I square it. If there's a b times x plus h, I distribute the b, and so on. That gives me this term. I cancel all the terms that I'm adding and subtracting, which will always be the highest power in x in every constituent term in the function. So I cancel 3 of those. Here, here, and here. I should get a different color. I canceled this one, I canceled this one, and I canceled that one. And then I'm left with only 3 terms. And this step, I have those 3 terms here. Now I can divide through by h to get rid of the h's on all the next highest terms, because the next highest powers in x will have a single h attached to them. And if that's not clear to you, square some x plus h's, and you'll see soon that the way they all work, they work in a very particular pattern. A pattern that we'll see more when we do explicit derivatives of powers of functions in the next video class. When we derive the rule for powers, we'll see it's just a matter of multiplying out x plus h's, right? X plus h squared, x plus h cubed, and so on. Okay, so now we have this one. And now, sorry, I have this one over here. Now, powers, lower powers than the next highest power. So in this case, the 0th power, x to the 0, which is a constant, they'll have h's left over after you divide through by 1h, and all those will vanish in the limit, leaving you with just the derivative itself over here. And that's it. We've taken the derivative of any quadratic function from first principles. What is it? Well, the derivative of that function is actually a function itself. There's a constant term, just like there was for a linear function, but there's also a term that has an x in it. Right? So the derivative of the function actually changes as you change your value of x. So for instance, if I had a parabola, if my function up here, the f of x, were a parabola that looked like that, right? The slope of the function is getting less and less as you move to x equals 0 and eventually hits 0, or b in this case, if there's a b. So the slope of the function is changing with x. And that's the power of the derivative. It's pretty easy to just eyeball a linear function and say the slope is 7. It's a lot harder to compute the slope of a nonlinear function at every point just from drawing a whole bunch of secants and tangents, right, and taking limits. The derivative gives you the function that represents the slope of the line at every single point on the line. And what that does on the curve, and what that does is tell you the point at which the slope is 0, which is we'll see when doing optimization in a few video lectures, is the important thing we're trying to find. The point at which the slope of the curve is 0 is going to be a critical point of the function. It'll be related to the first order condition that we'll solve to get that point at which the slope is 0, and that point will have a lot of meaning in a bunch of different applications, both in game theory and statistics, and we'll talk a lot about that when we get to optimization in a few video lectures. But the key now is to recognize that computing these derivatives from first principles is always possible. It might be incredibly messy, but it's possible. So I'm going to do a couple more to get used to this before we move on. Okay. Here's a messier one. I'm going to skip some steps here because it's messier. Let's just try x cubed. Well, we have x plus h cubed minus x cubed, the limit of that, over h as h goes to 0. There's our derivative again, just plugging it into the definition of the derivative. And the problems for this video lecture, there are opportunities for you to do this yourself. Well, what does that equal? I can expand out the x cubed. Let's do it in stages. There's an x squared of it. There's another one. I'm going to drop the limit for the moment just because I don't want to keep writing it. As you'll find in going in this video course, I'm lazy like that sometimes, but just keep in mind there's still a limit here. What's that now? Well, we can expand that again. We get x cubed plus 2x squared h plus xh squared plus xh plus 2xh squared. So that should be x squared h. What am I doing here? No, that's right. Sorry, I missed a square here. That's the problem. So that's x cubed plus, plus x squared h. Sorry, I lost my train of thought here. X cubed, 2x squared h, x squared, plus xh squared, yes. And then x squared h plus, that's right, plus h thing. This, I must apologize, will happen sometimes when you're writing on a board, even on a piece of paper. Sometimes you get ahead of yourself. It's worse on a blackboard, as you find out, or a chalkboard, a whiteboard, or whatever, or a tablet in front of a video camera. So I'm going to apologize for that, but I'll make sure to correct them as I go. Okay, so here is the full expansion minus x cubed divided by h. Now there are a lot of terms here. It might seem kind of messy, but let's just work with it. So first note that the x cubed, the leading term, cancels as it always is going to do. And I should stop for a second. If that expansion gives you more trouble than it gave me, and you saw it gave me a little trouble, it's just practice. What you want to do is make sure that all possible combinations of distributed values get multiplied. So multiply these two, these two, these two, these two, these two, these two. So there's 6 terms there, right? Sorry. So there's 6 possible terms, 6 possible combinations of the product. So you must include all of them, and you can count. There are 6 terms in this sum. And there are tricks to go faster with this, but this way you can see where it came from. Okay, so that's the first term. It goes away. Now I said before that the next term, the most important term, is going to be the one with a single h in it, the next leading term. So let's get those together. So we have over here, we have 2x squared h. Over here we have x squared h. Together they make 3x squared h. Okay, now next leading term, we have xh squared and another xh squared. So you have plus 3xh squared. And finally, there's an h cubed. And we divide all that by h. Okay. Well, these h's go away. This h squared goes away, becomes an h. And this cubed becomes a squared. Now what do we see here? Now let's put the limit back in again. We have the limit of 3x squared plus 3xh plus h squared. Well, there's no h in this thing, so that sticks around. The h in this thing goes to 0, so that term goes away. And the h in this thing goes to 0, that definitely goes away. And finally, we're left with 3x squared. So the derivative of x cubed is 3x squared. Now, if you're really good at patterns, you might have seen a pattern already here. The derivative of x squared was 2x. The derivative of x cubed is 3x squared. That's actually true. And we'll see in the next video lecture that the derivative of any power of x is just the power times x to the power minus 1. And we'll derive that more generally in a technique just pretty much like this one, exactly. But that's how it works. I'll do one more example that's a little more complicated before ending. Okay, so what if your function is a little more complicated than a power? What if it's 1 over x? Well, how would I do that? The same exact way. So limit as h goes to 0 of 1 over x plus h minus 1 over x over h. This is messier in a sense because there's two quotients on top. Let's multiply out. Let's combine them. X minus x plus h over x times x plus h divided by h. So what I did was, sorry, let's read parentheses. I combined those two things. If you want to see that in a little more detail, what I did was this. I multiplied the one on the left, top and bottom, by x. I multiplied the one on the right, top and bottom, by x plus h. And that allowed me to combine the two of them. All right, that's how I got that thing, this thing over here. Okay, so now what do I get? Well, the x's cancel, and I get negative h over x times x plus h times h. Right? The h's cancel, and I put the limit back in again. I get the limit. Again, the limits here always, I'm just dropping it because writing on this tablet is kind of a pain in the neck, so I'm trying to minimize it to minimize possible errors I make as well. But the limit is always there. Okay. The limit is the limit of negative 1 over x times x plus h. Well, if you recall our rules of limits, the limit of a function on top over a function on bottom is the limit of the function on top over the limit of the function on bottom. The limit of negative 1 is negative 1. The limit of x times x plus h is just x squared, because the h just goes to 0, and I'm done. The derivative of 1 over x is negative 1 over x squared. And that's it. And again, this follows the same pattern actually. You can write 1 over x as x to the negative 1. Well, I said the derivative of a power was the power times the power x to the power minus 1. Well, that's negative 1 times x to the power minus 1 is x to the negative 2, which is just this. So it's the same pattern. That works for all but 0. But we'll get to that in the next video lecture. But that's it. You can calculate the derivative, potentially using a bunch of work, of most of these things just by going back to first principles, and we'll derive a few more in the next video lecture. But really, in practice in political science, the derivatives you'll be taking tend to fall into a small number of categories, either a polynomial or some quotient of polynomials, or an exponential, e to the x, or a logarithm, log of x, or some more complicated functions made up of constituent terms that are polynomials or exponentials or logarithms. So what we're going to do in the next video lecture is show you exactly how to calculate those, first by calculating individual pieces of those, and then by using rules to deal with more complicated derivatives. But really, what it comes down to is everything, the rules, the derivatives themselves of the constituent functions, they all are derived from this first principle, going back to the definition of a derivative. In practice, if you're really good at rederiving rules and things, you can get everything you want from the definition of the derivative itself. And that's it. That's how to calculate derivatives. I hope that was useful. The best way to do this is practice. It might not be clear at first, but I guarantee you, if you keep practicing, try different functions, you will eventually get good at that and find it much easier, and a lot of the mystery will go away. Because really, there's nothing to a derivative, which is half of calculus, right? Other than just trying to understand the instantaneous slope of a line, which you compute by taking a secant and taking the space between the secant points closer and closer and closer together until you have a tangent point at that line. The definition of a derivative is just that. There's nothing else to it, nothing fancy, and you can compute derivatives just by applying that definition. And that's it. And that's most of this video lecture. There's one more module ahead in which we'll give you a little prelude of part 5 of the class of multivariable calculus. There'll be some stuff you'll see probably pretty early in political science that will use multivariable concepts, and I want you to have some basis in understanding those before we go on to part 5, in case your particular math course doesn't actually get to part 5. Well, thank you very much, and I'll see you in module 6. Thank you.